today we are going to discuss about compactor and further how that EDT DRCs will be there. Okay, what kind of DRC design rule checks are applicable on the compression insertion. Okay, so let's see. So compactor. So we have a decompressor, chains, subchains, the small chains, compressor chains, okay, and compactor. So compactor, again, it is a kind of a mux, okay, mux kind of a structure, but not a mux, okay. Now there is a masking logic. We'll discuss that. Lockup cells followed by XOR gates. We'll have multiple XOR gates. Okay. So we'll try to, XOR is very helpful in filtering two inputs. Okay. So XOR behavior. What is the behavior of XOR? The truth table of XOR? Anybody? The logical behavior of an XOR gate.
One input is 1, the output is 0.
Are you sure?
Yes, sir.
Any one input is high, then what is the output?
No. Output is
0.
low.
Okay. So what is the behavior of NAND? What is the behavior of a NAND gate?
When two inputs are high, then the output is low.
When two inputs are high,
Output is 0.
Then the output is low.
so previously we have said for XOR NAND behavior you told for XOR and XOR behavior you told for NAND. See, XOR gate is when you have any one input high, then output is high. That is XOR. XOR, right? XOR behavior is any one input is high, the output is high. NAND gate, any one input is high, then the output is 0. Correct? Is it correct or wrong? Are you guys able to recollect the truth tables? NAND gate behavior is opposite of AND gate. So any one input is high,
Yes.
the output is 0. XOR gate, any one input is high. Okay, no,
Then
sorry.
the output is 0.
Any one input is high. That means only one input should be high. Then the output will be high. Only one. Either of the inputs, only one input should be high for XOR. Not both the inputs. Only one input. If at least one input is high in XOR gate inputs, then output is high. That means 1. So that is more helpful. That behavior is helpful, irrespective of. So the other input, if one input is high, obviously the output will go high. Okay, so this will be able to help us pass a value. Okay, That means you need to pass a value through one gate, a high value. Okay. So other value, you don't. I mean, it's a, for example, it's a don't care or a X propagation value, any value. Okay. And the other input is high. Okay. You should be able to, the tool should be able to, the gate should be able to transit that one value to outside. Okay. But in compression, we have a different scenario where we want to bring out the values from this particular two chains connected to one XOR gate. So from this chain, when you're trying to shift out, okay, when you will collect the value from here during shift out, right? Shift in will be capturing, shift in will place values in the chain, capturing will capture the value, okay, and next shift out will happen, right? So in this scenario, you are trying to capture the shift out value to the outside. I mean, you are trying to push the value to the outside. So when you're trying to push the value to the outside, these two chains again has to be concatenated to a single chain. I mean, single output. Okay. And again, these two outputs again concatenated to one more XOR. So the XOR chain, the level of XOR gates will increase depending on the number of input subchains and number of output channels. Okay. So ultimately, you want to bring out how many channels you have, that through that channels only you have to capture all the chain output. Okay. So only XOR gives you the benefit. Okay. So XOR, we use XOR gate, and between XOR, in before XOR, we have a logic called masking logic. Masking logic is an AND gate. Okay. Additional AND gate. We'll discuss masking logic in a next in the second topic. First, we'll finish compactor, okay? And lockup cells is the same usage where to avoid any kind of delays, okay? Overcome any delays before the gate and after the gate. Okay. Now, so when you have this kind of structure and you're trying to capture this, okay? Let me show you the masking logic. Yeah. So masking logic is a AND gates. So you have AND gates because why you need masking logic first? The concept of masking logic. Okay. The concept of masking logic is that let me take an example. Okay. Like this, we have value chains. Okay. It's better to write. 1 0 0 1 1 0 1 1 1 0 0 1. Okay, this is one chain and there is one more chain. You are trying to feed into an XOR gate. Let's here 0 is there, X is there, 1 is there, X is there, 0 is there, 0 is there, 1, X, 0, 1, 1, 1. Now when you have this kind of environment, 1 0 XOR, what happens? 1. Okay, first value, output value is 1. 0 and X. When you have 0 and X, XOR behavior is X, because X can be 1 or 0, right? If it is 0, again the output should be 0. If it is 1, output should be 1 again. So output will change depending on the this value. So definitely you should have a known value when your output is other input is 0. Okay, so 0 and X in XOR behavior will get X. 0 and 1 1. 1 and X. 1 and X, what is the value?
X.
Everybody. Please answer, everybody. One and X, an XOR gate. What will be the behavior?
It is 0.
Explain. Y1, Y0 or YX. Explanation, with explanation. It is 1 or X. Hmm? So this value can be 0 or 1, right?
Yes, sir.
If 0, output is 1. When this X is 1, I mean this is going to be 1, then 1 and 1, again XOR output is 0.
0.
So there is a dependency on the one input. On the both the inputs, the XOR gate is dependent. So you'll get X. Again 1, 1, 1, 1, 1, 1X, X, 1, 1, 1, 0. Correct, right?
Yes, sir.
Now remember that these x values, you should not have x values in your pattern. Remember always that tool doesn't, ATE doesn't process x value. It will go to metastable. Okay. So we always make sure the pattern, there is a solid 0 or 1. On a physical level, tool doesn't understand x. Tool, no, not tool, the chip will understand x. Okay. It will consider it as a metastable. So when you have metastable data, not a stable data, your pattern will fail. Okay. So this particular pattern can cause nearby patterns to fail when you have X propagation in the chain, in the pattern. Okay. So the ones for the compactor, it is not good for comparison. Okay. So so your expected output is some 0 or 1, and you are getting simulated as X. Then you are not getting an accurate value. At least you are not getting an opposite value. You are getting completely X. So X's are not a valid data. So we need to have a valid data, either a 0 or 1. So in order for that, what we will do is we will add a AND gate. Okay, AND gate, and the tool will place the mask logic of 0 or 1 for the other input of AND gate. For example, if there is a X propagation, depending on the input value, okay, the other input value, this value will be programmed by the masking decoder and this hold register and a mask shift register. This entire mechanism will program the other input of AND gate. Is it clear?
Yes, sir.
So definitely when you have an AND gate, there is no output of X. AND gate behavior is when one input is high, okay, sorry, when both inputs are high, then only the output is high. If irrespective of this scenario, if any other input or output value, that means 0 or 1, then you are doomed. So when you have this kind of scenario, assume that AND gate other input will be 1. Okay, assuming when you have 1, X you have X now, X and 1. X and 1, what will happen for AND gate? Based on the truth, X. So when you give 1, you cannot get a value. So always the AND gate other input will be 0. Okay. Understood? Is it clear?
Yes, sir.
So when you have 0, irrespective of this X input, okay, this will be marked as, this particular output will be marked as output of this. So 0 and 0 will be 0. Okay. X and 0 will be 0. Okay. So wherever extrapolation is there, that will be masked with a known value. Okay. So that will be programmed. This value will be programmed when there is X propagation. When there is no X propagation, it will match the exact output. It will try to bring out the actual response value to the output. So when there is an X propagation, tool by default makes it a 0. Irrespective of 1 or 0, it will make 0. Okay. So these AND gates are added on each chain outputs, and we will mask the value. Masking means we are what we say in general language. Masking means so hiding the value, or in other words, we can say you are not the way for COVID. How you guys wear mask, right? Everybody has wearing mask, right? So similar way, we want to we don't want to pass the unknown value rather than provide a known value. So we are hiding the kind of a actual truth. So there is an expropagation, but we are trying to mask it and bring out a known value. Okay, so there are many strategies to avoid expropagations as well within the patterns. Okay, so we will discuss on how expropagations will come. Okay, that also we'll discuss. Why we will get an expropagation. Okay, why there is an x value captured. Okay, that also we'll discuss. So till this part, everybody understood?
Yes, sir.
Yes, sir.
Okay. So the detailed information of how this masking and all will be explained in these chapters. Okay. For now, we are discussing on the schematic and understand what is the internal structure of the schematic of the EDT logic. Okay. Now, yeah. Masking logic followed by XOR tree, XOR tree. After XOR tree, I mean group of gates combinedly we call it as a tree. Okay, XOR tree followed by we have output channels. In the output, you have a output bypass. Okay, so output bypass, whatever you have here. Okay, so you are trying to, if you want to enable bypass mode, you have to convert input bypass signal. I mean this muxing, input bypass muxing, and you have to have output bypass muxing also. Okay, so again you will have output bypass mux. These are the bypass muxes. Okay, so channel 4 and channel 1 merging together again channel 8 channel 2 merging it again. Okay, so func output from core again combined with this will give you EDT channel out 1, EDT channel out 2. So likewise we will try to bring out the original behavior of individual chains. Okay, so this could be complex, but don't what we call don't mess it up. Okay, it's simple. Trying to make the compressor chains back to stitching into single chain, the original chain. For that, you need to understand how many subchains we have made and this each mux, this diagram is very clear. Okay, if you understand this diagram, the each and every path you will understand. Okay. So nobody will ask what is that. Try to explain the behavior of bypass, but we can just say that compressor chains are routed back into single individual chains by using the mux structure, and mux select line being the bypass mode, EDT bypass mode, higher 0. Okay. So this is simple understanding of making it a little bit small. It's a simple having 4 chains, how muxes are added. Okay, so that it will behave like a original chain, starting from this to this, this to this. Just you can just understand, okay, how bypass is enabled. So without decompressor and compactor, the original chain, if you want to make, input 1 has to go directly to this mux, one input. Decompressor output has to go to one output. Again, this select line is always EDT bypass mode. Okay. So again, like this, same decompressor output and second chain. Okay. So this single chain mechanism is to convert into original chains. So if you follow up this schematic line by line, you'll get to know the connectivity. You can place one value and see you're getting the original chain formation or not.